Hi friends, welcome back to my YouTube channel. In this video, we will be discussing about some commonly used skill metrics or performance evaluation metrics, or which is also termed as forecasting indices. These metrics are used to compare the model predictions with the observations and to find out how good the model is. And this can also be used to find out the best model for the dataset by fitting a variety of models. And here I'll be discussing 20 skill metrics along with the formula and Matlab. So the notations are OI for the ith observation, PI for the ith prediction, where I equal to 1 to etc. n. And the corresponding averages are denoted by O bar and P bar, and the corresponding standard deviations are denoted by STO and STP. And K is the number of parameters used on the model. So the first metric we'll be discussing is mean bias error, or MBE in short. MBE formula is 1 by n summation I equal to 1 to n, or Pi minus y. So Pi minus y is the error or the bias, you can say. So mean of this, so 1 by n into summation. The next metric is mean fractional error. Comparing to other metrics which I'll be discussing, MFE is less commonly used. The formula is MFE is equal to 2 by n summation I equal to 1 to n, the absolute value of Pi minus y divided by Pi plus. The third metric is mean percentage error, or MPE for short. MPE is equal to 1 by n summation I equal to 1 to n. This error term, that is Pi minus y divided by OI to get the percentage, and then taking them. Now, if you need to convert this into a mean absolute percentage error, you'll take the absolute value of this error, then multiply by 100 to get the mean percentage error. So the mean absolute percentage error, or MAPE formula, will be 100 into 1 by n summation I equal to 1 to n, absolute value of Pi minus y divided by O. Now, the fifth metric is mean absolute error, and this is very commonly used in research. The short form is MAE, and which is equal to 1 by n summation I equal to 100, the absolute values of the error. The sixth metric is mean square error, that is MSE. MSE is very commonly used, and I think you might know the formula as well. And MSE is also used in training the neural networks. So the formula is MSE equal to 1 by n summation I equal to 1 by Pi minus y, the whole square, that is square of the error, and then taking the mean. The seventh metric is relative absolute error. So our AE formula is summation I equal to 1 to n. The absolute value of OI minus PI divided by summation of I equal to 1, the difference of the absolute values, the absolute values of the differences. So OI minus P bar is the mean. The eighth metric has root mean square error, and it is very commonly used. The RMSE formula is root of 1 by n summation I equal to 1 to n Pi minus y the whole square. So this term is nothing but the mean square error, and then taking the root to form the root mean square error. Now the researchers try to include a normalized version of this RMSE. So the normalized version is taking this RMSE, then divide by the mean of the observation. So this is the normalized RMSE. Now the 10th metric is root mean squared logarithmic error. So instead of this Pi and OI, here we'll be using log of OI plus 1 and log of Pi plus 1. So the remaining formulas is this. So root mean square logarithmic error, and this has been recently implemented by the researchers in finding the model accuracy. Now the correlation coefficient and coefficient determination is very commonly used. So the R formula is summation of I equal to 100 Pi minus P bar into R minus O bar divided by the root term. Summation I equal to 100 Pi minus P bar squared, summation I equal to 100 Y minus O bar the whole square. Now to find the coefficient of determination, we need to square this R, that is the correlation coefficient, and you'll get the R square value. Now, Nash-Sutcliffe efficiency is an important metric, and it is commonly used in research. So, NSE formula is 1 minus summation I equal to 1 to n Pi minus y square divided by summation I equal to 1 to n y minus O bar square. Now, a normalized version for this Nash-Sutcliffe efficiency has been used by the researchers. So the formula goes like 1 by 2 minus this NSE, which is the Nash-Sutcliffe efficiency. Now, the 15th metric is log-hyperbolic cosine loss. So this is a kind of loss function. So the formula is summation equal to 1 by log, then this is the hyperbolic cosine, as the name says. Then the error term, pi minus 1. Now, volumetric efficiency, the formula is V is equal to 1 minus summation I equal to 1 to n. The absolute value of pi minus y divided by summation I equal to 1 to y. And Kling Gupta efficiency, that is kg. For kg, we need to find out the R value. R value is the correlation coefficient. Then you need the standard deviations of the prediction and standard deviation of the observation, and mean of predictions and mean of observation. So you can find kg using this formula, which is 1 minus the square root of r minus 1 whole square plus the standard deviations percentage minus 1 whole square, average percentage minus 1 whole square. The 18th metric is redefined Willmott index. So this takes two form depending upon this condition. That is the condition where summation I equal to 1 to n. The absolute values of the errors is less than 0, 2 times summation I equal to 1 to n. The absolute values of OI minus over. So that is actually the deviation from the mean. So if this value is less than or equal to this value, then this is the formula. It is 1 minus summation I equal to 1 to n absolute value of pi minus y divided by 2 summation I equal to 1 to n modulus of y minus y squared. Now, if the reverse is the case, we will have this form. That is reversing this fraction, then minus 1. The next metrics are of information criteria, Akaike information criteria, which takes the form 2k. K is the number of parameters used to model, plus n, that is the total number of observations, logarithmic or natural log, summation I equal to 1 to n, y minus pi whole square. And for basic information criteria, it is k ln plus n ln, summation I equal to 1 to n, y minus pi whole square. So these are the metric, and you can see this is information criteria metrics, and the last metrics are of an index, whereas the initial metrics I mentioned is kind of error metrics. Now, each of the metrics has its own advantages and disadvantages. So we should be very careful while using them, and also try not to use similar or proportional metrics like using both RMSE and this NRMSE to find the model efficiency, or like both the mean bias error or mean absolute error. So the recent researchers has incorporated indices like this, the last discussed, that is Nash-Sutcliffe Efficiency, KGE, then VE or RWE, along with the error kind of metrics which I initially mentioned, to compare them. Now we'll go for Matlab code and the implementation. So here I have an observation. This is the observation, and this DB is the prediction. And I have formed all the metrics. So all the 20 metrics. So I'll discuss one by one. So first is the mean bias. So for some of the terms or some of the metrics, we need to create a function, while for some of the other metrics, they will have an inbuilt function. Like here you can see RMSE, which is already an inbuilt function. So you need not create a code for this error term or metric term. So then first one is the mean bias error. I'll show you the code. So this is the formula, the function for mean bias error. Now the second metric is mean fractional error. This is the function for mean fractional error. Mean percentage error. Mean percentage error. Now mean absolute error is MAPE. You can use it as an inbuilt function. Now for mean absolute error, absolute value of this. Yeah, mean percentage. Now this is for mean square error. It is an inbuilt function. I will go with relative absolute error. This is the function for relative absolute error, and you can change the names. I just named it sum, mean, white, pseudo, sum of the denominator, just like that. You can change according to your wish the variables you can assign. Now RMSE is an inbuilt function. Now for normalized RMSE, I used this RMSE and I created a function here itself. So divided by mean of the observations. Now next is the root mean square logarithmic error. So this is for root mean squared logarithmic error. Now next is correlation coefficient. You can use CORR to find the correlation coefficient. And you can just square it to find the R square value, that is the coefficient of determination. Now for NSE, this is the code for NSE, that is Nash-Sutcliffe Efficiency. Now normalized NSE. So this is for normalized NSE. This is 1 minus 2 of this NSE, that's it. Now log hyperbolic cosine loss. This is the function for hyperbolic cosine, log hyperbolic cosine loss function. Now the next is volumetric efficiency. Now this is the formula for volumetric efficiency. Kling Gupta efficiency, KG. So this is for Kling Gupta efficiency. Willmott index. Willmott index. Then AIC and BIC. This is for AIC and this is for BIC. Now let us run the codes. So this is our skill metric. So initial metrics are a kind of error. So the unit will be, suppose if you have the data set to be rainfall some in terms of millimeter per day. So this metric, skill metric unit will be kind of millimeter per day error metrics. Now, if you are going with indices, it will be like no units. So if you are writing a research paper, in the table you will have to mention the units if there is units for your skill metrics. We should not forget that. So this is our skill metrics. So thank you for watching and happy results.